Hello students, welcome back to the second part of our chapter Mechanics, Motion, Force and Equilibrium. In the last session, we studied motion, acceleration and Newton's three laws of motion. Today, we'll go a step further to understand force, momentum, impulse, equilibrium and stability with clear examples and numericals. A force is simply a push or pull that can change the state of rest or motion of a body. It can also change the direction or shape of an object. Forces are of two types: contact forces, where bodies touch each other, like friction or tension, and non-contact forces, where there is no direct touch, like gravitational or magnetic forces. Example: when you push a door open, that is a contact force. When Earth pulls an apple downwards, that is a non-contact gravitational force. If the total force on a body is zero, we say it is in balanced condition. If the total force is not zero, the body accelerates. This is an unbalanced force. Momentum represents the quantity of motion possessed by a moving object. It depends on both mass and velocity. We say momentum equals mass multiplied by velocity. It is a vector quantity, meaning it has both magnitude and direction. Example 1. A cricket ball of mass 0.15 kg moving at 20 meters per second has momentum equal to 0.15 times 20, that is 3 kg meter per second. Example 2. Numerical: suppose a car of 1000 kg moves at 20 meters per second. Its momentum equals 1000 multiplied by 20, that is 20,000 kg meter per second. If another car has half the mass but double the speed, that is 500 kg moving at 40 meters per second, its momentum is also 20,000 kg meter per second. So, two different objects can have equal momentum if the product of mass and velocity is the same. When no external force acts on a system, the total momentum before and after the interaction remains constant. Example: when a gun fires a bullet, both start from rest. The bullet moves forward and the gun moves backward with equal and opposite momentum. Numerical example: suppose a bullet of 0.01 kg is fired from a 2 kg gun. If the bullet leaves the gun with a velocity of 100 meters per second, then the gun recoils with velocity equal to 0.01 multiplied by 100 divided by 2, that is 0.5 meter per second in the opposite direction. The total momentum before and after firing remains zero, it is conserved.
Sir, does this law also hold true in space?
Excellent question. Yes, it does. Rockets work purely on this law. Hot gases are expelled backward, and the rocket gains forward momentum. This is why rockets can move even in the vacuum of space where there is no air. Impulse. Sometimes, a large force acts for a very short time but still causes a huge change in motion. This is called impulse. Impulse equals force multiplied by the time for which the force acts. It is also equal to the change in momentum. Example: when a footballer kicks a stationary ball, the contact time is just a fraction of a second, but because the force is large, the impulse is enough to send the ball flying. Numerical example: a force of 50 newtons acts on a body for 2 seconds. Impulse equals 50 multiplied by 2, which is 100 newton seconds. If the object's mass is 10 kilograms, then the change in velocity equals impulse divided by mass, that is 10 meters per second. Torque is the measure of this turning effect. We say torque equals force multiplied by perpendicular distance from the axis of rotation. Example: when you open a door, you apply force at the handle, far from the hinge, to produce a larger turning effect with less effort. That's why pushing a door near its hinge feels harder. Numerical example: a force of 10 newtons is applied at a perpendicular distance of half a meter from a hinge. torque equals 10 multiplied by 0.5, that is 5 Newton meters.
Sir, why do long spanners make it easier to loosen tight nuts?
Because increasing the length increases the perpendicular distance, the torque becomes larger for the same force. When all forces acting on a body cancel each other and there is no net turning effect, the body is said to be in equilibrium. The center of gravity is the point at which the entire weight of a body acts. A body is more stable when it has a low center of gravity and a wide base. Examples: racing cars are built low to prevent toppling. Gymnasts spread their feet apart to increase the base area for better balance. A stool with a wide base does not topple easily. Numerical example: suppose a uniform rod is 1 meter long and weighs 10 newtons. If a 5 Newton force acts at one end, the center of gravity shifts slightly toward that end, increasing the likelihood of tilting. To balance it, an equal counteracting torque must act on the opposite side. There are three main types of equilibrium: stable, unstable, and neutral. Stable equilibrium: the body returns to its original position when disturbed, for example, a pendulum at its lowest point. Unstable equilibrium: the body moves farther away when disturbed, like a pencil balanced on its sharp end. Neutral equilibrium: the body stays in its new position, like a ball rolling on a flat surface. Objects with low centers of gravity and wide bases are more stable. That's why double-decker buses have heavy engines at the bottom and acrobats bend their bodies while balancing. So students, in this class, we explored force, momentum, impulse, torque, equilibrium, and stability. We learned how to calculate momentum, how impulse changes motion, and how torque helps us understand rotation. We also saw why lowering the center of gravity and widening the base improves stability. These ideas apply everywhere, from bridges and vehicles to sports and daily life. Remember, balanced forces keep a body stable, unbalanced forces create motion. Keep practicing the numerical problems we discussed today. Understanding them deeply will make physics easier and more enjoyable. Thank you for your attention. Stay curious, keep learning, and Jai Hind.